Welcome to the first presentation in Unit 1 entitled, or excuse me, Unit 2 entitled Building Blocks. It says there are no elements so diverse that they cannot be joined in the heart of man. So, the learning objectives for this particular unit are that students should be able to demonstrate that all compounds are built from fundamental elements found on the periodic table, and they should be able to quickly recall the name or the chemical symbol of the most 42 most common chemical elements. It's a little out of order there. So it says chemistry, like all science, is dependent on measurement. That's something that we really focused on in Unit 1. Can you measure it? Can you convert it? Can you graph it? Once you graph it, can you find the relationship between those? There are limitations to how small we can make measurements and how large we can make measurements. So as a result, you can measure objects indirectly if you cannot measure them directly. So in the lab, you should have figured out that there's a limit to how far you can break an object down. These limitations can occur due to your tools. You can't tear a piece of paper up, keep tearing it, keep tearing it, keep tearing it until you have specifically tools that are able to do smaller and smaller that your fingers aren't able to. So you have limitations because of your tools, and you have physical limitations too, in which it can no longer be done. You've reached the limit at which it occurs because the object can no longer be reduced. So, big idea one in chemistry. We're going to focus this unit on the three big ideas, and these big ideas are things that are going to occur in every subsequent unit. Every unit from here to the rest of the year is going to focus on these big ideas. So, whenever we go through new content in Unit 3 and 4, I want you to say, well, how does Unit 3 line up to these big three ideas? How does Unit 4 line up to these big three ideas? How does Unit 10 line up to these big three ideas? And the first one that we're focusing on this time is that all matter is made up of a limited number of elements. The arrangement and interaction of these atoms determines the properties of an object on a macroscopic scale. So, the macroscopic behavior, when you look at lead and you say, wow, that's a block of lead, the fact that it's soft, the fact that it's dull, the fact that it's metal, the fact that it conducts electricity is entirely dependent on the atomic structure. Okay, the arrangement of those lead atoms determines the macroscopic properties of the object. So, what's matter? You should be familiar with matter. You've talked about matter in just about every grade in science. But matter is anything that has mass and takes up space. So, in other words, it has a measurement that we can make in grams, and it has volume. And in chemistry, we tend to focus on the grams or it to be in milliliter, although sometimes it would be in centimeters cubed. And those are actually the same thing. 1 centimeter cubed is 1 milliliter. So mass is measured in grams or kilograms. Like we said, it's most often going to be grams. Volume can be in liters, it can be in centimeters cubed, it can be in milliliters, but those are the two requirements for an object to have matter. So coincidentally, that's why light is not considered to be matter, because light does not have mass. So if you have a particle of light, which we'll talk about later, is called a photon, that photon has no mass. Because it has no mass, we don't say that light is matter. So atoms. The term atoms comes from the Greek word atomos. Atomos means means not. So whenever you put in front of something, it means not. It means, and then tomos means to cut. So whenever you say atomos, it means you cannot cut it. So because of that, atoms is a philosophical idea that you eventually reach the point in which you can no longer cut something in half. Now there is some experimental evidence that we'll get into for the atom, and that's going to be the focus of Unit 3. So you can break an atom down, you can cut it in half, but at that point it loses its identity. So once it loses its identity, we say it's no longer what it is. That's why it's considered to be an atom. So an atom is the smallest fundamental unit of matter that retains its identity. Chemical symbols and elements. So there are over 60 million chemical compounds that have been identified and registered. As an example of that, you could have something like this: C8H18. That right there is octane. And octane is the primary ingredient in gasoline. If you notice, you wouldn't find octane on the periodic table. Instead, what it is it's a combination of two different elements. So that's what we mean by compound, when you have a combination of elements to make something new. All of these compounds are made from just 118 elements on the periodic table. In fact, some of those elements on the periodic table aren't in any compounds at all. The vast majority of the things that occur in compounds are going to be our 42 common elements that we're going to refer to later. But all elements have the same name. Okay, so they're all helium atoms. They have the same chemical symbol, which is this He. they have the same atomic number, and they have the same average atomic mass. We need to make sure we put that in there, that it's going to be the average atomic mass. Okay, and we'll talk about why it's the average atomic mass and just not just atomic mass when we talk about the atom itself. So today's periodic table. You should be very familiar with the periodic table. It is basically a cheat sheet for all the material that we're going to cover in chemistry. If you can understand the relationship on the periodic table, you can get so much more information than you could by trying to put it on a little note card to cheat on a quiz or a test. Today's periodic table is organized by atomic number, which is the number of protons, but once again, we'll talk about that later. There's a lot of information, and then we highly suggest that you go to ptable.com and you bookmark it, because ptable.com has information on every single element, all the rows and columns, every trend, every property, whether it's electronegativity or ionic radius. All of those are available on ptable.com, so we highly suggest that you go there and bookmark it. Atomic mass is displayed at the bottom of each element, and it refers to the grams per mole, or it can refer to the atomic mass units. So if I were to have one boron atom would have a mass of 10.86 AMU. If I were to have 1 mole of boron atoms, it would have 10.86 grams. So those two things are the two scales that you can use for this number depending on what you have. If it's asking about an individual atom of boron, you can use AMU. If it's talking about grams or moles, you can use the other one. But both are the same. It's the same conversion factor. Now these are the 42 most common elements in chemistry that you use in introductory chemistry. You are responsible for knowing the symbol and the name. Okay, you don't have to memorize all 118, but these are by far the most common ones you will see. And so when you see something like this, you shouldn't say carbon, sulfur, fluorine. You should know that CS is going to be cesium and that this is going to be fluorine. You need to know these 42 elements moving forward. It will appear on your quizzes, and it is the expectation that you know these moving forward. We highly suggest you make note cards or you practice with a partner, but these are things that you have to know moving forward so that you can focus on the chemistry later instead of, hey, what does H stand for again? So, using a periodic table, what is the chemical element name of V? Now you'll notice V is not one of your 42 most common elements. So if this is not one of the 42 common elements, I would expect you to be able to use the periodic table to identify the V, and then once you find the V, look underneath the V for the name. The name in this case is going to be vanadium. Okay, so if it's not one of the 42, you should be able to use your periodic table. If it is one of the 42, it's the expectation that you could say, like if I were to say, what is O, you should automatically say oxygen without using a periodic table. Okay, it says a 10 atom sample of a substance is identified to have 320 protons. What is the identity of the sample? Okay, now remember, every element on the periodic table has a specific number of protons for every atom that is there. So what I want to do is I want to take my 320 protons and I want to divide it by the number of atoms. The reason why I want to do that is that'll tell me the number of protons, 32 protons, that every one atom has. So now I can look at the periodic table because the periodic table is displaying information for one atom. So now I would need to go to my periodic table and I'd say, okay, what is the one element that has 32 protons in it? And so you look at the atomic number. You'd start here with hydrogen, it'd be 1. Helium would be 2. Sodium would be 3. Beryllium would be 4. Okay, boron is 5. Carbon is 6. Nitrogen is 7, oxygen 8, fluorine 9, and so on and so on and so on until you get to 32. When you get to 32, you would look it up and you say, oh, that's germanium, Ge, or germanium, which is a semiconductor that is often used in computer chips. It says, what do you think are the most abundant elements in the universe, in your body? And then there's a specificity, okay, in your body by number and in your body by mass. And there's a little difference there. Okay, now if you were to look at this, it kind of depends on how you look at it. You see it, here's an example right here, and this is done by mass. Okay, you see that oxygen represents 65% of your mass, and carbon represents 18% of your mass, and hydrogen represents 10% of your mass, and then 3% hydrogen, and then the others make up the rest. So really, it looks like it's going to be oxygen. But then if you look, every oxygen that you have has a mass of 16. So when you divide that out, that's roughly 4 parts of oxygen. Where if you were to look at hydrogen, hydrogen has 10%, but every hydrogen atom only has 1, so you end up with 10 parts of hydrogen. So even though the hydrogen has much less mass, it makes up more by number. So this right there is actually hydrogen. This right here is going to be oxygen. And then finally, in the universe, it's going to be hydrogen for both. Okay, hydrogen is by far the most abundant element in the universe, making up well over 90% of the elements that are there. That's why our stars are made out of hydrogen. They're almost all hydrogen. And if you were to look at the mass of our solar system, people say, well, yeah, the sun is made out of hydrogen, but then you've got all the planets. All the planets would fit in a very, very small portion of the sun. The sun is by far much, much, much larger than all the parts of the solar system combined. So hydrogen is the most abundant element in the universe. Okay, so molecules. Some elements do not exist as one atom in nature. Okay, you will never go around and find a single oxygen atom floating around in the air. Okay, because oxygen does not exist as what's called a monatomic atom. Okay, monatomic, mono was one, atomic. Okay, so oxygen does not exist as a monatomic. Okay, helium does exist as a monatomic. So there are certain elements that do not exist as a monatomic, they exist as diatomics. And the way that you can memorize that is Brinkelhoff. Okay, Brinkelhoff is something that we're going to reference throughout the year, but it represents the elements that exist as diatomics. So you would never see bromine floating around in the air by itself. Instead, you would see bromine gas, which is Br2. You would never see nitrogen by itself. You would see N2. You would never see oxygen by itself. You would see O2, and so on and so on, so on and so on. The other way that you can memorize it is it's called the 7 at 7 plus hydrogen. Okay, and if you look right here, if you start at atomic number 7 and you were to draw the number 7 on the periodic table, that right there is the same elements of Brinkelhoff. Okay, you have your bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, but then you have to add the hydrogen at the end. So the 7 at 7 plus hydrogen, or Brinkelhoff. Okay, compounds are combinations of two or more, and here's the key, different atoms. So when we have O2, that's not considered to be a compound. But when we have the substance CO, which is carbon monoxide, it is considered to be a compound. So compounds have to involve more than one type of atom. There are over 60 million compounds that have been registered, and many of these compounds do not occur in nature. In fact, this is one of the most exciting aspects of chemistry is the idea of materials chemistry. Okay, if you were to look at the biggest difference between your life now and life 100 years ago, it's all about the materials that were used to construct things. Plastics did not exist. A lot of our, Kevlar, a lot of the polyester, the material that people wear, they didn't exist because they don't occur naturally. So materials chemistry is by far the aspect of chemistry that has changed your life more than anything. A lot of people think it's going to be things like computer chips or cell phones and those sorts of things. But without the materials to house and make the chips for those, there's no way that those devices could exist. Okay, if you were to look at the devices that are the materials that are built into your phone, without developing those materials, you would never have those devices. Now, the smallest molecule that you can think of is going to be hydrogen. Diatomic hydrogen, because hydrogen is a Brinkelhoff, has an atomic mass of 2 AMU. Okay, if you were to look at its next closest competitor, helium has an atomic mass of 4. So because of that, diatomic hydrogen is going to be by far the smallest molecule. Okay, that's also one of the reasons why hydrogen will actually rise. If you ever produce hydrogen, it goes up. That's why they used to use hydrogen for balloons. Okay, we use helium now instead, even though it's a little bit heavier because it's not flammable. But you have two very, 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 very small, and this should say atoms, two very small atoms that result in one molecule. This represents one molecule. The largest compound that we know of so far is the idea of this protein called, I think I'm pronouncing it right. It's Titan. Okay, kind of like the planet Earth. So it says that's the largest known compound. Now, if you were to look right here, this is a protein. If you were to look in biology, everything that you talked about in biology for the most part last year, cellular biology occurs at a microscopic scale. Okay, and you had your cell, and then you had your organelles, and then these tiny things right here, you had little proteins. Okay, and remember, this whole thing is microscopic because this is a cell. If you were to think about this, the largest compound that we're talking about is right there. And it fits inside the organelle, which fits inside the cell, which is microscopic by itself. So when we talk about compounds, we're talking about things on a microscopic scale. This is the largest one that we've come up with, and it has 169,723 carbon atoms alone. It has 270,464 hydrogen atoms alone, and it goes on from there. So think about how massive this compound is, and then realize how small it is in the grand scheme of things. So atomic mass. Knowing the atomic mass is not enough to identify a substance. For example, if you had an atomic mass of 28, it could be C2H4, N2, or CO. And here's the reason why. A carbon atom has a mass of 12. An oxygen atom has a mass of 16. So when you add those together, you get 28. Nitrogen, there are two nitrogens that are each 14. When you do that, you get 28. And carbon, there are two carbons that are 12 apiece, and there are four hydrogens that are one apiece. And remember, I'm getting these numbers from the atomic mass, and when you add those up, you get 28. So atomic mass cannot be a property that is used to identify a compound. Okay, you have to look for other things. There's macroscopic properties and microscopic properties, but mass is one of the things that can put you in the ballpark, but it's not enough to be able to identify a substance. So it says identify the number and type of atoms in the molecule below. If you were to look, we can write this out. You have 12 carbon atoms. You have 22 hydrogen atoms, and you have 11 oxygen atoms. Okay, that's what these numbers represent. This is called a subscript, and it tells you how many of each type of atom there are in a compound or a molecule. Next, it says how many different compounds do you think can be made using only the currently known elements on the periodic table? This is kind of an opinion related question because we already have 60 million plus, 60 plus million. But if you look, there should be nearly an infinite amount depending on the circumstances. These elements that we have right now are not, these are highly unstable, so they tend to not react. Okay, but under certain circumstances, you can get nearly any atoms to combine under the right circumstances. And then the final question, it says, why do you think Brinkelhoff elements do not exist as a single atom in nature? And the reason is because atoms seek to be in a stable state. Okay, if you have a single oxygen atom, it is highly, highly, highly reactive. Okay, in fact, it has a special name. It's called a free radical oxygen. Okay, and because of that, it's highly, highly, highly reactive. It will react with anything. So really the only way to have a single oxygen atom is to have nothing else around it. Okay? By taking another oxygen atom and putting it with it, it makes it stable. So what that actually does is, and we'll talk about more about this later, but it lowers its energy level. It makes it much more stable, much more relaxed, much less reactive. And so because of that, that's why these Brinkelhoff atoms exist as diatomics instead of monatomics.